Welcome to the deep dive. Today we're looking at some notes that connect pure maths, calculus specifically, with something very real, growing plants.
Yeah, it's about figuring out how we can use these mathematical tools to understand, well, a key aspect of agriculture.
Our mission really is to see how calculus helps solve practical problems. And the problem here is quite interesting.
It is. The sources focus on trying to estimate the total light energy that a crop canopy manages to intercept, over a specific time period.
Yeah, right, not just the light right now.
Exactly.
Yeah.
Because think about it, the sun's brightness, it changes all day, the angle shifts, you get clouds.
And the plants themselves are growing, changing shape. It's not static.
Not at all.
Yeah.
So if you're, say, a farmer or maybe a scientist building a model, you really need that total figure, the accumulated energy.
A single snapshot just won't do the job. You've got to sum up all those little moments of light capture, hour by hour, day by day.
Mm-hmm. And this is exactly where the notes bring in calculus, specifically integration.
Okay, integration. So differentiation gives you the rate of change, right? Like speed at one instant.
Precisely. But integration, that's the tool for adding up something when its rate is constantly changing. It gives you the total accumulation over an interval.
So let's say you have a function like ft that describes how fast the canopy is grabbing light at any moment t. How do you get the grand total from, say, time A to time B?
That's the definite integral. You integrate that rate function, ft, over that time interval, a to b.
And the answer you get, that's the total light.
That's the total accumulated light energy intercepted, yeah. Mathematically, it's the area under the curve of that rate function. But physically, it represents that total energy capture.
What I found interesting in the notes, though, is that getting that function, that ft, isn't trivial. It's not just pointing a light meter up.
Oh, absolutely not. The sources touch on the complexities. You have to model how light actually gets into the canopy.
Like how many leaves are there?
Exactly. Things like leaf area index, basically, how dense the leaves are. And even concepts like the Beer-Lambert law, which describes how light gets absorbed as it passes through layers, like layers of leaves.
And the sun's angle, how the crops are planted, all that geometry matters for the instantaneous rate.
It all feeds into defining that rate function, ft. So you're combining field measurements, maybe some ecological principles, modeling.
And then you bring in the calculus, you integrate, you go from the rate to the total.
That's the power right there. Moving from the rate of change to the total sum accumulated. That's the fundamental theorem of calculus in action, really.
It makes the whole idea of finding the area under a curve suddenly very practical. You're calculating actual energy for plants.
And that total number, it's crucial. You can use it to predict how much the plants will grow, their biomass, or figure out watering schedules, since photosynthesis and water use are linked.
Or even compare different ways of planting things.
Yeah, planting densities, different varieties perhaps. It gives you a solid quantitative number for decisions that might otherwise be more, guesswork.
I think for anyone listening who's maybe studying calculus now, wrestling with derivatives and integrals, this example really makes it click, doesn't it?
I hope so. You see derivatives as rates, integrals as accumulation, and boom, here it is, measuring sunlight for crops. It's not just abstract math.
It shows these are real tools for solving complex, real-world problems. Agriculture, environmental science, loads of fields.
Definitely.
Okay, so let's wrap up this deep dive. We've seen how figuring out total light for crops is, well, a perfect job for integration.
Right. It lets us sum up that constantly changing rate of light capture to get a really vital total number, linking the math to actual plant growth.
And seeing how all those factors, leaves, sun angle, everything go into finding the rate first, then using integration for the total, it really shows how useful this is.
It's a neat application.
It does make you think, though. What else is out there changing constantly? Like river flow, maybe? Or chemical reaction rate? Forest carbon uptake? How could integration help us measure their total impact over time?